VIP. All right, so our derivative rules. We don't have a lot of background about why these kind of are what they are. I'll try to give a little bit of, I did mean MVP. Did not mean VIP. Wow. Okay, anyway, so I'll give you a little background about why these kind of first ones, make sense. But the ones that we get to, probably not today, but on Wednesday, it's a little bit of kind of trust and believe in a way. But anyway, so let's look at some of our first derivative rules. So the derivative of a constant. Now I'm going to write these derivative rules in Leibniz notation, just because it's just easier to write them out in Leibniz notation. So say I want to take the derivative, which is what this is saying. This is just saying take the derivative. And say I want to take the derivative of just some constant, just some number, any number, no variables, just a number. The derivative of a constant is 0. And so again, I'll give a little bit of background on these ones. If you think about it, what we're doing here, remember the derivative is a slope, which I've been trying to nail into your head so much. The derivative is a slope. So if you think about a constant function, so it's just a straight horizontal line, what's the slope of that function? Excuse me. What's the slope of that function? The slope of that function is 0. So that's why the derivative of a constant is 0. What about the derivative of a linear function? And let's say that I just don't have a y-intercept on it. So let's just say it's some m times x. So I have some, some linear function that just goes through the origin. Well, what's the slope of that line? Well, it's the slope of the line, which in this case would be m. So if you ever want to take the derivative of something that looks like a constant times x, your derivative is just that constant. Sorry, something's weirdly happening in my throat. All right, and then this one you kind of just got to trust and believe. If we want to take the derivative, and we'll be doing lots of examples in a second, if we want to take the derivative of essentially two functions that are either added or subtracted together, what we're going to do is we're going to take the derivative of the first function. We're going to add or subtract it to the derivative of the second function. Goodness gracious. So essentially we can, it's almost like you can push that derivative idea through like addition and subtraction. You just take the derivative of each piece. And then if you have a constant times a function, so say you want to take the derivative of some constant k times some function f of x. Essentially what happens is the constant can kind of come out front and then we just take the derivative of the function. You'll hear me say a lot of the times that the function comes along, the constant comes along for the ride. It just kind of tags along and we just have to worry about the derivative of the function. So this is our first set of derivative rules. Now, so essentially when we look at these things that we're going to want to try to differentiate, find the derivative of, however many other ways I can phrase it, we're going to use these rules. Yes, you will need to memorize them, but they're going to be used so often that they should hopefully start getting memorized pretty quickly. And that's another reason why I suggest going through that worksheet as much as possible when I put it up, because the more practice you get, the better you get at it. So let's look at some examples. So I want to differentiate these functions. So essentially, Grace, it doesn't, it's kind of whatever we want it to be. She asks us the variable for a constant c or k. Like I could have made this first rule the derivative of k for a constant, and I could have made it a c in the one below. I probably should have stayed consistent. You know what, let me change this one to a c. I'll stay consistent and make constant c, but technically it doesn't matter. It can be whatever variable I want it to be. All right, so say I want to differentiate the following function. So I have a function that's just 175. Well, that's just a number. So that's just a constant. There's no variable there. There's no x, there's no t, there's no whatever. So since there's no variable, I just have a constant. The derivative of this function, which remember I can also write as f prime of x. So the rules don't really write themselves very nicely in terms of this notation for these first couple. But remember that we can use, you could also have written dy over dx if you like Leibniz notation better. But the derivative of this function, since it's just constant, is going to be 0. Ooh, this chapter is going to be really hard to just do at a screen and not being able to read your faces. Anyway, I'm going to go to the right. So I'm going to go to number 3 next. So please feel free to stop me at any time if you have a question. And please ask me questions if you have them. This stuff is going to be used so often that you don't want to wait until later when you realize, holy crap, I'm lost in the exams tomorrow. So ask me questions along the way. Yeah, so why is it a constant? There's no x here. There's no variables. So since I don't have any variables floating around, it's just a straight number, 175. That's why it's a constant. It doesn't have any variables attached to it at all. So as opposed to number 3, where we have 19x. So now we have there, so it's not just a constant. So now we kind of have this kind of second rule situation going on, the derivative of a linear function. So I have some m times x. Now I used m in that one because that's usually how you write a linear function, mx plus b. We just didn't include the b in that one. So m being our slope here. So then our derivative of this guy would just be 19. So the derivative of something times x is just that number. Maybe I should also write down something that people forget a lot. And I'm going to write it in red. Maybe not red, maybe blue so it'll stand out. So kind of side note, that also means that the derivative of just x is 1. Like that falls under this format. You just usually don't write the 1 in front of the x, but that's one that a lot of people seem to forget for some reason. So if you have the derivative of just a variable by itself, it's 1. Okay. So again, I'm going to go over to the right. So number 5, here we have f of t. So if I have a t, that's going to be my variable. If I don't have a t, then it's just a number. So for this one, now this, we essentially use that derivative of a sum or difference. So we essentially just say, okay, well, I can take the derivative of the first thing. So what's the derivative of 2? 2 doesn't have a variable attached to it. It doesn't have a t, so it's just a constant. Derivative of a constant is 0. And then I'm going to add that to the derivative of 6t. What's the derivative of 6t? Well, we're in that case of something times a variable. So the derivative of 6t is just 6. So the derivative in general is just 6. Now I'm going to be writing these out kind of in a lot of generality for the first little while, so that you realize, like, technically, once you get good at these, you can just jump straight to saying that the derivative is 6. You don't have to write down 0 plus 6 equals 6. You can just say 6 if you recognize that that's going to happen. But I want to make sure to try to keep track of exactly what I've done. Technically, we need the derivative of 2 is 0 and the derivative of 6t is 6. Okay. So I want you all, I'm going to give you like a minute to look at these. They kind of mirror the ones above it. The last one's a little tricky. But I want you to look at these. I'm going to give you a minute before I talk about them. And I want you to try. And this is going to be awkward because I hate just sitting here in silence. But, you know, it is what it is. Oh, yeah. Just trying to keep the rules in there, but there we go. Let me Still try to keep the rules in there and still have it. All right, couple more seconds. All right. Oh, I have to put the drawback on. Draw. So the derivative of -2 is going to be 0 because -2 is just a constant. There's no variable there. Derivative of -27t is going to be -27 because we have something times a variable, and just I should stress that it's because it's just t, because we're going to see in a second that we're going to have things that are like a number times t squared or t cubed, and that's different. But if it's just t, just x next to a number, then the derivative of that is just the number. And then for this last one, derivative of 25x is 25. The derivative of pi is a number, so its derivative is 0. So the whole entire derivative is actually just 25. Questions, concerns about any of those? Because we're about to step it up a little bit. Tiny bit.
So basically, oh, I have a question. I forgot to raise my hand. So that's what I'm just getting is that, like, if it's constant, or if there's no variable attached to the constant, then it just kind of goes away.
Yeah, essentially.
Okay.
Because the derivative is 0, so it just kind of, yeah, goes away.
Okay. Thank you.
Yep. Will there be a case where the b is not equal to 0? What capital B are you talking about?
She means like the constant, I think.
Oh, so the derivative of a constant, just a number by itself, is always 0. The only time it's not going to be 0 is if there's a variable attached to it. If it's just a number by itself, always going to be 0. Oh, wait, no, maybe you meant this? Or maybe not, I don't know. But if we wanted to say the derivative of a linear function that actually had a plus b on the back, whoa, I did that wrong. Whoa, just him. So yeah, if we have the derivative of a linear function, I can kind of step that up a bit, where we actually have that plus b. But that's kind of where this sum or difference comes into play, so we kind of don't need to think about it either, because then it's just the derivative of the mx and then the derivative of b separately. But I could also make it a completely entire extra kind of rule off to the side, where the derivative of a complete linear function, even with a y-intercept, is still just going to be that slope of m. But this kind of extra rule is kind of these two rules kind of just smashed together. All right, moving on. The power rule. So this is our first kind of official rule. So we have that the derivative of some x to the n. Now, this rule is going to come into play a lot, because the rule that I just wrote down was just an x to the n, but we're going to have things like 2x cubed, 2x to the 4th, 5x to the 7th. And we're going to be using this kind of constant rule where we just kind of, the constant just kind of comes along for the ride. But we'll see that in a minute. So the derivative of some variable to a power you're essentially going to bring the power out front and subtract 1 from the power. So I'm going to write that in words. You'll hear me say a lot, bring the power down and subtract 1 from the power. I taught high school a couple years ago, and when I taught them this, they decided to lovingly call it the yeet it and drop it. So if you want to refer to it as that, go right ahead. So that was fun because in the middle of class, I'd be like, what are we doing next? And they're like, yeet it and drop it. And I was like, I can't handle you. So that was a fun time of my life. Anyway, 2 things that you're going to want to remember, kind of side notes. Side note. Some exponential things that you're, exponential rules that you're going to need to remember. If we have a root and a power, possibly, let me make that a bit clearer. So n is the root, and we might even have a power in there of m. This is equal to x to the, it's essentially the power over the root. So if we have something like the square root of x, that will be x to the 1/2. If you have the cube root of x, it will be x to the 1/3. And the other thing is if you have 1 over x to some power, this will be equal to x to the negative that power. So those 2 kind of exponential rules are going to come into play a lot when we're doing these derivatives. So let's look at some of these guys then. So we want to find these derivatives. So for the first one, let me zoom out a little bit so I can get all of these in here while keeping the rule on there. Scroll down the tiniest bit. That'll be enough. So say I want to find the derivative of x to the 8th. So I want to take, and I'm going to split, accidentally run into my other problem. So if I want to take the derivative of this, well, what I'm going to do is I'm going to take that power and I'm essentially going to bring it out front. Exactly, Kayla. And then we're going to subtract 1 from the power. So we would have 8x to the 7th. And again, I'm being super general. I would never write this if I was doing these by hand. I would just jump straight to writing 7. That doesn't look like a 7. But if you need to do that, go right ahead. Is it going to fix my 7? There we go. So that would be 8x to the 7th, and that would be our derivative. So now I'm going to go down. So I'm going to go the correct order this time. So for the next one, the first thing we need to do, or should do, I should say, is we need to get it into kind of this form. We have x to a power. We have 1 over x to a power. So we can't use the power rule yet. So we need to use that kind of one of those side note things that I noted. So this would be equivalent to x to the negative 3rd. I have not taken a derivative yet. Have not taken a derivative yet. A lot of people get confused and they think that just rewriting it like that is the derivative. No, no, no. All we've done is written a completely equivalent thing. So now I can take its derivative. Oh, come on. So bring the power out front. Subtract 1 from the power. So negative 3 x to the negative 4th. And I'm just going to keep pausing for a slight moment afterwards in case there are questions, but then I'm just going to keep moving on. So for the next one, we still don't have that form yet. So I should change this to be written as x to the 1/2 first. And again, at this point, have not taken a derivative yet. I've just written a completely equivalent thing. And now that it has the correct format, we have x to some power. I can take its derivative. Bring the power down. Subtract, whoops. Subtract 1 from the power. Nope, that's backwards. Subtract 1 from the power. Technically would like to write it underneath, but I've run out of space. 1/2 x to the negative 1/2. Oh, I should be careful with that fraction while we're getting too far. Scroll down the tiniest bit. That's too far. Oh, come on. Sit down. Tiny bit. Come on, you can do it. There we go. You can leave it like that. That's perfectly acceptable. If you would like to change that back to not have a negative exponent, feel free. But you can totally leave it as 1/2 x to the negative 1/2. That's usually how I would leave mine. But whatever floats your boat. All right. So next one. So now we have not just x to a power, but we have this constant out front. So if I want to write this out in full generality, what we're going to do is that 2 is just kind of come along for the ride, kind of. And then I have to multiply that by the derivative of the x to the 4.5. So the derivative of x to the 4.5 would be bring the power down and subtract 1 from the power. So if I multiply those two numbers together in the front, 2 times 4.5 is 9, and x to the 3.5. Once again, once you've been doing these for long enough, writing out that first step is tedious, so you can totally just jump to the last thing if you want. No matter how much, write out as much as you need to, by all means. If you need to do that for the rest of your life, go right ahead. But don't feel like you need to do that many steps for me. Like you can totally jump from this to the derivative, just straight out 9x to the 3.5 if you would like. This next one, pause for another second. One unnecessary step, but I'm going to do it anyway just in case, would be to rewrite that, because x squared over 4 is equivalent to 1/4 times x squared. So if I want to take the derivative here, that 1/4 comes along for the ride, so it just kind of sticks around. And then I have to multiply that by the derivative of x squared. Derivative of x squared, bring the power down, subtract 1 from the power. Add that to the derivative of 3. So we had to keep going. But remember, we can essentially just kind of push through addition and subtraction. So the derivative of 3 does not have a variable attached to it. It's just a constant, just a number. So the derivative of 3 is 0. 1/4 times 2 is 2. X to the first. So we usually don't write the little 1. If you want to, go right ahead. And then the plus 0 just kind of drops. I'm going to give you a minute and a half to try 6 and 7, and then we'll go through 8 and 9 together. So I'll sit here awkwardly for like a minute and a half. Where'd the 1/4 go? No, wait, no, that's wrong. Someone call me out on that. That's not 1/4 times 2 is 1/2, not 2. Oh, Sam did call me out on it. Thanks, Sam. No, totally, I botched that. Sorry. 1/4 times 2 is 1/2, not 2. So that should be 1/2 x for number 5, not 2x. Holy cow. Sorry about that. Thanks, Sam. I didn't see your message, but thanks for catching that, because I am dumb, apparently. All right, couple more seconds. All right. Number 6, that -3 essentially comes along for the ride, and then if you do your power rule, you will get, well, -3 times -4 will give you +12, and then you'll have x to the, oh, my pen's starting to freak out, to the -5th. -5th? Yeah, this one. My arithmetic is so bad. 7 is one of the longest one we've seen so far, but it's the same idea of kind of behind number 5, is you just kind of keep taking each piece as it comes. So what's the derivative of x to the 4th? Bring the power down, subtract 1. Whoops, I'm getting ahead of myself. I'm really not used to doing the full steps right now. So bring the power down, subtract 1 from the power, plus the derivative of 2x cubed. 2 comes along for the ride. Bring the power down, subtract 1 from the power, and I'm going to run out of space. Plus the derivative of 5x, which is just 5. Plus the derivative of 4, which is 0. So 4x cubed plus 6x squared plus 5. For number 8, we should rewrite first, which means we haven't taken a derivative yet. Why am I doing a plus? Because those first 2 terms are not in the correct format. Again, once you get really good at these, you can kind of start doing them in your head, and you don't necessarily have to write that extra step of showing me what it is actually equal to. So our derivative here, so I have x to the 1/3 because I had a third root. So bring the power down, subtract 1 from the power, add that to the derivative of x to the -2nd, bring the power down, subtract 1 from the power, subtract the derivative of 5x, or if you want to think about adding the derivative of -5x, whatever floats your boat, that would be just 5. So we would have 1/3 x to the -2/3. Always got to think about those. Minus 2x to the -3rd minus 5. Right, 1/3 minus, yeah. And then for 9, we have x to the pi. So x is a variable, pi is a number, so this is okay. Bring the power down, subtract 1 from the power. And this one you just kind of have to leave as pi minus 1. And that's how the power rule works. Questions, concerns on the power rule before we go on to some more different rules? Got it. Okay, we're doing all right on time. On 8, yeah. So, whoops, scroll. First thing we need to do is just rewrite this. So since we have x to the 3rd root, that is equivalent to x to the 1/3. So whenever you have a root, that's equivalent to x to the 1/n. So that's an equivalent statement. Okay, I'll get that in a second, Gwen. And then we also have that we want to rewrite 1/x squared if we have 1/x to a power that is equivalent to x to the negative power. So that's why we get this -2 here. And then the minus 5x is just minus 5x. So now that we have this in the right format, we can take its derivative. So this, what I have there boxed is equivalent to the original function. We haven't done derivatives yet. So now I have a couple of power rules. So I want to take x to the 1/3. I want to take its derivative. So my power rule tells me to bring that power out front. Here it is. And then I have to subtract 1 from that power. So 1/3 minus 1. And then I have to add that to the derivative of x to the -2nd. Power rule tells me bring that power out front. There it is. Once it catches up with me, there's my little line. Little line, there it is. So bring the power out front, subtract 1 from the power, so we have x to the -2nd minus 1. And then we have to subtract the derivative of x. So the derivative of 5x, since it's 5 times a variable, and there's no, oh, side note. Let me do a side note down here. If my pen will work, we can actually view the derivative of some constant times x as a power rule as well. If you think about this, this is technically x to the 1st. So if I wanted to take the derivative of this, this might be a little, maybe I'm going a little too far, but oh, if we were to do the power rule on this, we would bring the power down and subtract 1 from the power. So we'd essentially get c times x to the 0. Anything to the 0th power is 1, so that's just that constant value. So that can be another way to think about it if you don't want to try to treat it as its own rule. That's technically a power rule. But since it's just a number times a single occurrence of a variable, the derivative of 5x is just 5. And then I just rewrote it on the next line, just cleaned it up a little bit. 1/3 minus 1 was -2/3. -2 minus 1 is -3. Does that help, Kayla? Clean this back up. Gwen, why was the first pi we talked about equal to 0, the derivative of it was equal to 0, and this one wasn't? Notice this pi is by itself. There's no variable attached to it. It's not attached to anything else. It's just by itself. So that, as it stands, it's just the number pi. But in the one we were just looking at, the pi was the power. So now it's a power of a variable. So it's not just pi by itself. Since it's attached to that variable, it's a completely different rule. But no, that was a good question. Any more questions before we move on? All right, we've got some more rules coming at us. So we want to take the derivative of some a to the x. This is a number to a variable. The power rule, so kind of side note, the power rule is a variable to a number. They're different. So do you have a variable to a number or a number to a variable? So if we want to take the derivative of some number to a variable, this is one of the really big trust and believe me, it's going to be equal to the natural log of a times a to the x. More importantly, this one we'll use amounts of the time. We will use more often a very specific case of this, which is when we have e to the x. So if you think about it, since the natural log of e is 1, the derivative of e to the x is e to the x. Like everyone's best friend, because it just stays itself. Everyone loves that rule. Or maybe they don't, I don't know. So those are technically the same rule. This one is just this very specific case of it. And this one is the one we're going to use more often. We are going to use this a to the x rule in some of the problems below, but in terms of like exam questions and quiz questions, I rarely ever use that a to the x. I always use e to the x instead. It's more often used. Now, say I want to take the derivative of some e to the kx. Well, no, I have k there, so I have to be constant with what I wrote in my notes. Sorry about that. K is a constant here. If you want to write c instead, go right ahead. Now I want to be really careful here. Why your book presents this rule at this moment in time, I don't know. So I'm going to write off to the side. Technically, a chain rule. Now you don't know what chain rule is yet. Well, some of you might, but we don't know what chain rule is yet. And I'm going to stress it a ton when we get there. Because it's presented as a rule here. And I don't know why, because it's technically a chain rule. But anyway, this is going to be essentially you bring that constant out front, but then leave the e to the kx alone. So it's like you bring the power out front, but then you don't touch anything else. And then the derivative of the natural log of x is equal to 1 over x. That one's like the weirdest one, I think, just because the form changes so drastically. 10 minutes. You should hopefully get through this first then. So, I should zoom out a little bit so I can keep these rules in here. Zoom. Zoom. Oh my god. Zoom. All right, so let's see some examples. Yeah, let's split this up again. Oh, no. And we'll just leave it like that. Okay, cool. So, first one. I want to take the derivative. I have 2 times 3 to the x. Please do not make that 6 to the x. That's not how that works. It has to stay 2 times 3 to the x plus 5 e to the x. So I'm going to start way over here so I don't run out of space. This 2 times is the constant times that function 3 to the x. So that 2 just comes along for the ride. Now I've got to take the derivative of 3 to the x. Well, that's an a to the x case. So my rule above tells me that the derivative of that is going to be the natural log of 3. Don't crap out on me now. Times 3 to the x. And then I have to add that to the derivative of 5e to the x. That 5 comes along for the ride. Oh my god. And then the derivative of e to the x is e to the x. Oh my goodness. I don't know why my pen is starting to crap out. So actually, I can't reduce that. It kind of just has to stay like that. Well, I guess if you wanted to multiply 2 in the natural log of 3 and write a decimal, that's fine, but we'll just leave it as it is. So the next one, if I have the derivative of e to the x, so I have essentially, what was that? I just did something. Well, that's a, no, go away. Okay, anyway, so the derivative of e to the x is e to the x. And I have to add that to the derivative of 2 to the x, which my rule tells me is the natural log of 2 times 2 to the x, plus the derivative of 7 is no variable, so that's just a number, so the derivative of a constant is 0. So of course you can write it without the 0. Well, as that. I'm unfortunately going to have to scroll down past these rules because I want to do the first column of this and the first column of the next bit because we haven't gotten to any natural log pieces yet, and I want to do that before we end. And then we'll hit the second column on Wednesday to start. So if I want to take the derivative of number 3, I need to take, now we're kind of lumping in a bunch of the other rules as well. It's the derivative of 8x squared. 8 comes along for the ride. Bring the power down, subtract 1 from the power. I'm no longer going to be writing the subtraction, but if you need to, go right ahead. 2 minus 1 is 1, so I'm just going to write 1. Plus the derivative of 8 e to the x. 8 comes along for the ride. Derivative of e to the x is e to the x. Plus the derivative of 8 times 4 to the x. The 8 has to come along for the ride. Derivative of 4 to the x is natural log of 4 times 4 to the x. So really the only thing we can rewrite is that first term, if my pen will let me. Questions, concerns on any of those? All right. So let's do 3 that include, let me try to leave that last one in there. That includes some natural logs here now. And then again, we'll hit that second column on Wednesday. So if I want to take the derivative of the first one, I need the derivative of 5 times the natural log of t, so the 5 comes along for the ride. The derivative of the natural log of t is 1 over t. Plus the derivative of 7e to the t. 7 comes along for the ride. Derivative of e to the t is e to the t. Minus the derivative of 4t squared. 4 comes along for the ride. Drop the power down, subtract 1 from the power. Minus the derivative of 12. There's no variable attached to that. So the derivative of just 12 is 0. You can rewrite this if you wish. You can leave it as 5 times 1 over t as well. I just usually write it like 5 over t. But whatever floats your boat. Next one. Going the tiniest bit quick because we're running out of time. I don't want to get these last 2 in. But still feel free to stop me. It's okay. Derivative of 160, there's no variable attached to that. It's just a number. The derivative of a constant is 0. Plus the derivative of 3t squared. 3 comes along for the ride. Bring the power down, subtract 1 from the power. Minus the derivative of 2t, which is just 2. You can treat that as a power rule, and you would have t to the 0 if you wanted, which is 1. So 2 times 1 is 2. Plus the derivative of 2 natural log of t. 2 comes along for the ride. Derivative of natural log of t is 1 over t. Rewrite this if you want. 6t minus 2, and I would write it as 2 over t, but again, you can write it as 2 times 1 over t if you like. With just these generic derivative questions, you don't really have to simplify them, but in chapter 4, we're going to need to do some other stuff with them, so you usually want to get used to simplifying them at least a little bit. And then the last one we'll do is this number 3. This one's got a tiny trick in it. And it's a trick that I, nudge, nudge, wink, wink, like to do every once in a while. So first thing we need is the derivative of 4e to the 3rd. There's no variable in that. This is just a number. There's no t. It's not e to the 3t. It's not 4t. There's no variable in there at all. That's just a constant. Derivative of a constant is 0. Plus the derivative of 2.5 natural log of t, 2.45 comes along for the ride. Derivative of natural log of t is 1 over t. So this is just 2.45 over t. Questions, concerns? Is there a variable in there anywhere, Kayla? And I'll hit that in a second, Jackson. So notice, Kayla, there is no, so the variable we're working here is t since it's f of t. There's no t in there at all. It's just 4e to the third. There was no t in there when I read it at all. Since there's absolutely no variable. Yeah, no, it's okay. So that's one thing that a lot of people do forget. E, whenever you see an E, it's going to be the number. I will never, and almost anyone will never, use E as a variable. E is a number. So since that's just a number, it's just a number. And again, I like to do that a lot. Anyway, do we ever have to solve for ln numerically? No, not in these cases. Slightly confused by your question, but no, the answer in general is just there's nothing. We're not. So it's kind of funny. For some reason, I feel like a lot of people get into a feeling that they need to solve everything, even if there's nothing to solve. This happened on the first exam with my composition questions. The thing we're finding here is just the derivative. So we're not solving for a variable. We're not finding a value or anything like that. We're just taking a derivative. So we don't have to solve for any, just finding the derivative and calling it a day.
Okay, what I kind of meant was like, do we ever have to like simplify ln with like a calculator or anything like that, or just leave it as ln?
Juliana, yeah, I totally forgot to put that up. I'll put that up later today. I'm trying to think ahead. Possibly in chapter 4, but I don't feel like we do a lot with natural logs in chapter 4. So I'm still leaning towards no.
Okay, thanks.
Yeah. So in chapter 3, definitely not. Maybe in chapter 4, but I don't think we do a lot of those with natural logs. All right, we're officially overtime. So if you'll need to leave, feel free. If you have any questions, feel free to stick around for a little bit. I've got a little bit of time before my next class. Otherwise, have a good day. I'll see you on Wednesday. I forgot to mention the quiz. I'll just talk about that when I put that worksheet up on Blackboard that I talked about. I'll send that out in the email that I send out later today. It'll be on derivative rules though, so. Let me stop the recording.